that you will have
Yes,
to
please.
talk, and basically it will be like a general impression about your PhD thesis.
Yes, exactly.
Okay.
Yeah. So thank you for being here, and I will present you so my PhD project in general, but there are two talks. So this first talk would be about like the first thing I did, which is this Banach algebras, which are acting on the Bergman space. And then this is like one of the most important part of my project. And then in the next talk, we will see how this can be extended and what work in the future can be done. So let's begin with the Bergman space. I will present you just the well-known facts about the Bergman space and Toeplitz algebras. We will introduce these quasi-radial symbols, then these pseudo-homogeneous symbols, and all those families of symbols. And then we will see the Gelfand theory and some applications of it, including the radical and other properties. So let's just begin with some well-known notation. We will denote like this the unit ball of Cn. We will consider the L2 spaces with this weighted measure with lambda greater than -1. We consider the weighted Bergman space. We consider the orthonormal basis of normalized monomials, the Bergman projection, and of course the Toeplitz operators, which will be denoted like this. Okay, so there is this well-known result by Professor Quiroga Barranco and Professor Vasilevsky, which says that in this Bergman space, when we have a maximal abelian subgroup, the set of, with some other conditions, the set of bounded symbols which are invariant under this set give rise to commutative C-star algebras, which are commutative for each lambda greater than -1. And so this result made us think that maybe those are all algebras, but no. So there is one general construction with them. The idea is to construct Banach algebras, which are still commutative, but are no longer C-star. And the idea is to take some subalgebra of these C-star algebras. In general, is to take this quasi-radial construction, but in the different context. So we take one of those C-star algebras, and then we take some special Toeplitz operators whose symbols are quasi-homogeneous or pseudo-homogeneous or generalized homogeneous, etc. And so these Toeplitz operators are not normal in general. So that's why the C-star algebras are not commutative, but the Banach algebras are. And that's also the reason why the Gelfand theory is the main tool to understand these algebras. So these quasi-homogeneous symbols are defined like this. So we decompose all tuples of Cn in groups. And so for that, we take some integer m, which would be the number of groups. We take a tuple of k's, k1 to km, which will be the length of those groups. And of course, the sum must be n. And now we decompose all tuples like this. The idea is somehow to work with each group in general and just then to put things together. And okay, so these groups will be given by this notation, and they will live in CKJ. Now we consider the groupal radius. So the radius that depends only on each group. And so the first symbols that we can define here are the so-called K quasi-radial, which are in particular subordinated to the quasi-elliptic group. And that's why this So if we consider the sister algebra generated by this by Toeplitz operator with these symbols, this algebra would be commutative. But that's not the whole story. We can even show that the eigenvalues functions and that one gets depend only on this. Sorry, this is wrong. This depend only on M. So you take in general in general, this is the formula for the quasi-elliptic group or the symbols that are subordinated to that group. But in this case, the symbols, this eigenvalue function only depend on these groups like this. And so when we consider the sister algebra, it will be a sister algebra of functions defined on C to the M, C plus to the M.
So multiplicity appears here.
Yes, yes, exactly. And it will play a role in the next steps. So we will denote by KQR, this sister algebra. And so here is what I told you. This is a algebra of functions which are indexed by this C plus to the M. And so this algebra is not so well understood so far. There is this question whether this holds, whether this is the linear closure of those operators, like not the algebra, but the closure, like what happens when we take separately brittle symbols. It's an open question. And one of the reasons why this could be is because there is also some kind of slowly oscillating property, but I think it's by now not well understood. But well, one can prove that also. But what one gets is that this algebra is a commutative sister algebra, which can be thought of as a algebra of continuous function acting on some compactification of this set. And
Miguel,
yes.
Miguel,
yes.
As far as understood, there's still open question how characterize this kind of slow oscillation.
Yes, yes. The problem here is that
do you have any progress in this direction?
Not really. I mean, I've tried to solve this problem, but I think I've got some ideas, but they seem to be complicated because for the case of just real symbols, I think the trick is to take this Laplacian and to calculate the Berezin transform, and then you get some formulas, and then you take some limit. But in that case, there is only one direction. In this case, there are M, so it's not clear really where to go and how to go. Yeah, so that's the main problem. And even the condition here is not, for example, just in one dimension, the condition looks, I think it was like this. This minus gamma of n. Here n plus 1. Then, oops.
Yeah, the problem here is the variety of directions. Yes,
exactly. So here is, I mean, maybe it's not trivial, but one can imagine how this behaves. But in this case, instead of this, one has some sum with some gammas, and here all the possible directions minus gamma of alpha plus something. So this is really complicated. That's the main problem. But I think that trick about the Laplacian could be used here also. It's just that it's not clear right now. Yeah.
But it's a good question to think about.
Yes, it is. Yeah. And okay, but what we know, and it's not hard to prove just by using some Weierstrass, is that this algebra can be thought of as some algebra of continuous function and some compactification of the set. This is not so hard. And so this is the only thing that we need to study the this Banach algebras. And so we proceed to describe how this set, what this set looks like. So for this, we consider the invariant subspaces of this algebra, which would be this span of the monomial such that the length or the such that the homogeneous degree in the J group is equal to Kj or kappa J. And we will also consider the direct sum in one direction. No, sorry, the other way around. We fix one direction and we consider the sum over all the other ones, which would be just this set here, this space here. And so this would play an important role in this case. Just a little spoiler, I will study the same problem in the Hardy space. And in that case, this, I mean, we can define this space, but the orthogonal projection is not in the C-star algebra. So that makes things harder. In this case, fortunately, it's not like this. So we can, without any problem, consider this orthogonal projections. This P kappa is in the C-star algebra. I think, yes. So this P kappa is in the C-star algebra. This is not so hard to see because, as I told you, this is some algebra of continuous function on that compactification. So any function that vanishes at infinity will be there. And it turns out that the orthogonal projection onto the subspace is also in that algebra. And that's not a trivial fact. And that's exactly why things don't work on the Hardy space. Because to prove that this operator is in that algebra, one has to take some trick with the Bergman transform for different weights, which you cannot do on the Hardy space because each weight is fixed in some sense. So that's the difference, the main difference. But anyways, we will see that this projection plays a role in this case.
Am I right that we show this for Bergman's space with Wolfram?
Yes, this is in your paper with Dr. Bauer. It's called, I think it's in the paper where you studied this Banach algebras, the first one, I think. Yes, this is not real, but it holds. The main problem here is that so the idea in some sense is not hard to understand because this comes from a Toeplitz operator whose symbol is K quasi radial. The problem is that symbol is in L1, I think, it's not bounded. So one has to do some tricks to prove that Toeplitz operator is in the algebra. Yeah. So in particular, we can use these projections to decompose the maximal ideal space. So they separate the points. So P kappa separates the points, the finite points, and Q can in some sense give us the coordinate at the J position of a point at infinity. So that's what we will do now. For that, we will consider different directions of infinity. So by using those projections and by using nets, one can see that each point in this compact set of maximal ideals can be reached by different directions. And that's how, so we describe it like this. We will consider this set of zeros and ones. And we will think that when theta j is 1, then that point, that coordinate is finite. And when theta j is 0, that coordinate is infinite. So I will describe this here. So this set can be decomposed as m theta, where the points at theta are reached by nets, such that this coordinate goes to infinity if this is in the complement. So if theta j is 0. So the decomposition, I think, is not hard to understand, but the notation is, one has to do this whole thing. So one has this proposition, or this formula, by using the projections p kappa and qj. One can prove that the maximal ideal space can be decomposed like this. And so first we decompose just with the direction at infinity. And once we are there, we can even consider or we can know which coordinate corresponds to which finite points. So this is what this kappa theta means. When we have a point such that there is some finite coordinate, for example, this j, then there is only one kappa j, such that this projection gives us 1, which means that in some sense, so for example, this would be some tuple, like maybe some infinity or something like this. And then in the j coordinate, it would be kappa j. So in this case, by the way, our theta would look like this would be 0. I don't know what else, and this would be 1. Okay, so this part is important because one needs to understand how this behaves when we combine it with the other quasi-radial or pseudo-homogeneous or all that stuff operators. Okay, so this is the first part of this algebra. So just to remind you, the recipe was this, some sister algebra, and then this quasi-homogeneous symbols. So that's the sister algebra, and now the quasi-homogeneous symbols. So for that, we need some more notation. We will decompose each group of the tuple like this. So first of all, we write it somehow in polar coordinates, just with respect to this subgroup. And then that thing we get, this xi, we write it as this decomposition, each tuple once again in polar coordinates. So we do all this because we want to introduce some symbols which are invariant when we act under this part here. So that's why we do all this. And so the symbols I will work with in this part of the project are the by now so-called generalized homogeneous symbols, which are symbols that only depend on this tuple Sj, and such that they are invariant under the unit circle like this. So this G acts on each entry, and it should be the same thing. So this is almost the symbols that we saw, I think, last year by Professor Quiroga. The difference is that in that case, this Sj is more general. It's only so we can change here. Instead of this, we can put this tuple here. With M, and so it's shown that this also gives rise to Banach algebras, which are commutative for each lambda. But this case is a little bit more complicated. I have already some results here, but the problem is that there is some tensor product decomposition that I'm using for these pseudo-homogeneous symbols, which doesn't hold in general for these kinds of symbols. But well, so we will consider these symbols, which are in their turn a generalization of previous symbols, which were which started with these quasi-homogeneous symbols and pseudo-homogeneous symbols, and so. So here is a how this was done in previous works. So for each group, we can take these quasi-homogeneous symbols, which are of this form. So we take this xi, which were given by this formula. We consider two integers like this, two positive integers, which are orthogonal to each other. So this means only that we take, so I don't know, 1, 0, 1, or so. So for example, for P and for Q, we take here 0, 1, and so on. So we take, so to say, normal numbers for some entries and conjugate it for the rest of them. So it's easy to see that these symbols fulfill this condition here. And then there came another generalization, which was this, let's say, classical homogeneous symbols, which are given by this formula. You take any bounded measurable function b, which depends only on Sj, and you take this tuple of t's here, and you make it to the power of some tuple p, such that the sum of the entries is 0. So it's similar to this thing we have here. In some sense, one has also this normal number in some entries and conjugate in the other ones. But this B makes it more general. And for some special B, you get the quasi-homogeneous symbols. So then I developed the theory but for a slightly more general kind of symbols, which are these ones. These are, so you take a pseudo-homogeneous symbols like this. You take the conjugate, and then you perturb this symbol by adding x times this conjugated symbol. So this is a interesting problem, because we have a family of algebras such that when x is 0, we get the normal Banach algebra by these pseudo-homogeneous symbols. And when x is 1, then we get the C-star algebra. So there was this question that what happens with the radical, for example, when we go from 0 to 1 and so on. Okay, and now our new symbols, which are this generalization. So we take it turned out that the only thing we need from all these symbols is this invariance on this part. Okay, so these are the previous symbols, and now this part is important to do some computations. It turns out that for these kinds of symbols, and that's why it's important to consider this part just depending on Sj, you can decompose the whole Toeplitz operator as some tensor product like this. So you just take a unitary operator which takes basic element to basic elements, even if the Bergman space has not a nice tensor product structure as the Fock space. So this makes sense in that case because of two things. Because the expressions you get only depend on the groups, on the J group, and because it doesn't depend on the weight. So when you do the computations, the weight just disappears, and you can even take here tensor product of weightless Bergman spaces. So this means that you can think of your Toeplitz operator with this pseudo-homogeneous or generalized homogeneous symbols as a tensor product where it's just the identity, and in the J entry you have the Toeplitz operator whose symbol is given just by the same formula, but in some sense restricted to the Bergman space on this ball of dimension kj. So this has some other explanation, because we saw last year that if you take those more general symbols here, then one can prove that there is some restriction, which would be, by the way, well, I write it here. If you restrict the Toeplitz operator with this more general symbol to H kappa, then this is unitary equivalent to some tensor product of matrices, like this. So matrix here, tensor identity. But the difference is that in that case, this matrix depends on the whole kappa. So you cannot move, so to say, without changing that matrix. And in this case, our matrix doesn't depend on the other, so it only depends on kappa j, so that one can, in some sense, factorize the whole tensor product. And that's why one gets this decomposition here. Okay, so this is also one way to see that this TCJ commute when, say, J prime is different from J. Okay, with respect to this decomposition, we will consider the invariant subspaces that one gets in each coordinate. So we consider this bold H, which would be just the span of this basic elements whose length here is D, but just in the Bergman space in the ball Kj. We can consider then for this operator that one has here, one has also its decomposition. In this case, this is then just a finite dimensional matrix. And we have also orthogonal projections. This would correspond to, just so to say, the finite factor of the infinite QD, so to say. And so we have this relation here. So our space, our infinite space in the other Bergman space is just the tensor product of these Bergman spaces with this finite dimensional space, and these H kappas correspond to the tensor product of this H kappa on each coordinate. Okay, so now we consider this Banach algebras, and in this case, one take one of these symbols for each group. I would like to mention here that this is a very general case, and that's why we need to take just one symbol for each group. The case of quasi-homogeneous symbols here, this case permits to take more than one operator per each group. But when you consider this generalized, or even from the pseudo-homogeneous symbols, the expressions are not so good to work with. And it seems that in general, there is no commutativity if you take, for example, two operators on the same group. So that's why we take only one, but most of the results hold in the same way. The only difference is that when you take the maximal ideal space on each group, then in the case of the quasi-homogeneous symbols, in this case, where I told you that you can put more than one operator, in that case, you get this joint spectrum, which it's not clear if is polynomially convex, and so that gives some troubles. But apart from that, it's almost the same kind of theory. So we consider this Banach algebra generated by the k quasi-radial symbols and by our simple Toeplitz operators, one for each portion j. And this algebra is commutative for each lambda greater than -1. And in general, if you extend it to a sister algebra, it's no longer commutative. And so one can easily show that the maximal ideal space of this algebra has to be, or can be thought of as a subset of this Cartesian product, where the left part is just the maximal ideal space of this algebra of k quasi-radial symbols, and the right-hand side is the maximal ideal space that one gets from the Banach algebra generated just by these operators. And so the first thing that one needs to know to understand this algebra is to know the Gelfand theory, and the first thing to understand that is to understand the maximal ideal space. So the first task here is to find exactly which points are in this space. And so we do it like this by means of some lemmas. So first of all, we take a point in the algebra here, and also this is from a previous version. This is also this is the whole algebra k quasi-radial set of homogeneous. You take a point in the maximal ideal space, and then you look at the directions of infinity that your point from the left had. So I mean, you take a point here, so mu would be here on the left side. You take zeta here, which would be here. And so the first thing to understand who zeta must be is to understand in which direction this goes. So we have this lemma here. As it turns out, when you take mu in this set, which means that when you take mu such that the coordinate kappa j is finite, so this is just a number, then on the right side, the j coordinate of zeta must be part of the spectrum of that finite matrix we saw. So this means that you cannot go to more than this finite matrix if you don't go to infinity on the left side. So the proof is like this, just a sketch. You can consider the characteristic polynomial of this matrix. You evaluate your Toeplitz operator with this polynomial, and then you multiply by this projection. And this is 0, because just by this classical Hamilton theorem, the matrix in that portion, in that finite portion, is 0. And with this projection, it makes everything outside of that portion 0. So the product is 0. And then you can evaluate this in this multiplicative functional. And then you get that P of that multiplicative functional is 0, which means that this psi of Tj must be in the spectrum, because it's a 0 of the characteristic polynomial. So this trick here, I mean, seems to be easy, and it's nice that this idea works also for the Hardy space, even though we don't have this q kappa j. Okay, but now, so long story short, you take finite coordinate for mu, then you have to take points on the spectrum of the matrix, which corresponds to zeta j. So what happens when we take kappa j equals to infinity, or what happens when mu is reached by a net whose j coordinate goes to infinity. So we get this here. In that case, this zeta j must belong to the polynomially convex fold of the essential spectrum. It makes sense because if you go to infinity, you leave behind, so to say, all finite matrices, and the only thing it remains is the essential spectrum. And since we are working with a Banach algebra, you must also have the polynomially convex fold. So the proof is like this. You take a point outside of this, but such that this holds. So I mean, such that the j coordinate of mu is infinity. And now we consider some perturbation like this. So the idea is that this set here is some the whole spectrum of TCJ. The whole spectrum looks like this. So you have the essential spectrum, maybe with some holes, and you have some points here. So these points would correspond to those points from the spectrum of the matrices that could not belong to the essential spectrum. So if you take the polynomially convex hole, then you just fill these holes. But these points remain here. And so you can perturb your operator by some finite rank projection such that these points somehow, you cannot make them disappear, but you can take them, maybe you can rotate them, or so it is not important, but you can do it in such a way such that the point that you have, it's not longer in the spectrum. But now this projection is of finite rank, and we are going in to infinity in that direction. So this multiplicative functional wouldn't detect this operator, or it would send it to 0 because it's compact. So what one gets at the end is that this part is 0. So you get once again this zeta j, but this should be in the spectrum of this guy. But we did it exactly such that it's not in the spectrum, so that this is a contradiction. So this means that if you take a point here, the only way you can get that point is if you go to infinity. So that's what this lemma says. And now, so what we know by now is, so we have done this. We have taken some points here, and we have tried to see what those points should look like. Now, the other thing we need to do is to see that those points are exactly in the maximal ideal space. So to do that, we use this tensor product decomposition, which this construction is it's a little bit long, but it's not so hard. The idea is just to take some eigenfunctions if you have a matrix, and to take a sequence that goes to infinity if you have if you want to have the essential spectrum. Let me well, yeah, I just write it maybe like this. So the idea is like this. We have this decomposition for our Toeplitz operators. And so if you want to have a eigenvalue here, you take a eigenfunction such that this gives you the eigenvalue. And if you want to have a point in the essential spectrum, you consider a sequence that in some sense go to infinity. So this is not that trivial, but this is done by doing some Bayesian transform trick. So you take some limit here, and you would get a point in the essential spectrum. So this would be 0. So you can take this construction at each portion, and then you just take the tensor product of the whole thing. And this would give you a net. In general, you can make it a net, not only a sequence, such that for any operator in the algebra, the multiplicative function of this operator has this property. So this means in particular that our psi of t would be the limit of this t, of this t, j, g alpha, g alpha. So this is how you approximate those points. So this means that you can make this whole construction be in the maximum ideal space. And then you just take the polynomially convex hull, and what you get is that exactly all those points are the points that we just saw in the other lemmas, such that you get this result here. The maximum ideal space is exactly this union here. So you take points on the maximum ideal space on the left. You see in which direction you go to infinity. If you go to infinity, you take points from the essential spectrum, from the polynomially convex hull of that set. And if you have a finite coordinate, then you take points from the corresponding matrix. And this whole construction, so you take the union over all possible points from the left, and then you get the whole maximal ideal space. So this seems a little bit complicated, but this is for the particular case, this is exactly what we have. For example, for the case of the quasi-homogeneous symbols, the maximal ideal space was something like this. M times, so for the case n equals 3, I think it was. So Z plus times 0 union points at infinity times some disk here of radius, I think 1/2. So this is exactly what we have in the just in this dimension. If you take a finite number, so an integer, then you have to go to the corresponding matrix.
This for two-dimensional ball or three-dimensional?
This for, yes, you're right, this for two-dimensional ball, yes. Yes. And so if you take a point here, then you go to the corresponding matrix. But for the quasi-homogeneous symbols, those matrices are nilpotent, so it's only 0. That's why you can, so to say, factorize the whole union, and you get all this set of integers, of positive integers. And if you go to infinity, which means if you take points here, then you go to the polynomially convex hull of the essential spectrum. In that case, this is just the closed disk of radius 1/2. So this is a generalization of that result. And okay, so that's the maximum ideal space. The Geffen transform is given by this formula. You take elements from the algebra of finite sums of finite products, and you evaluate on this set. So you take here diagonal operators in the Caesar algebra of K quasi-radial symbols. Okay, it should be here. Then you evaluate in mu, and you take these Toeplitz operators, this This is just some short notation for TC1 to the row 1 times TCm to the row m. You evaluate the corresponding zetas for these operators. So that's the Gelfand transform. That's the maximum ideal space. And now this is one of the important parts, but then with this Gelfand theory, one can try to find some structural information from the algebra. So that's the next part. Yeah, I think I have some time. So the first part, and it's one of the most complicated parts, is the radical of the algebra. For this, I needed to assume that this symbols Cj could be extended continuously to the boundary of Bkj. I think this could be somehow replaced by just oscillation property, but it's not so clear from the expressions. But so if we have this, then so the Toeplitz operator TCJ was once again this tensor product. So here this is acting only on the Bergman space on the ball Bkj. And so if we consider these symbols such that they are continuous on the closed ball, then of course we have these results about compacity. And so we can make some quotient such that we get a commutative sister algebra. But it should be then by some ideal like this, some ideal generated by operators of this form, where this entry is compact. And so this is one of the questions that was not so clear from the previous works, because there were some ideals who played some role, but it was not clear what the relation with the compact operators was. So this is the thing. If you think of tensor products, this is only the ideal generated by those operators such that the J factor is compact. So using this idea, we do this construction. We take Banach algebras generated by our operators, but only for a subset, not for all of them. So we formalize this by taking this theta, but this is only the idea. So when theta is 1, you take that operator. When theta is 0, you don't take it, so that you take sub algebras. Then we consider these ideals, which are related to what I told you. So J theta would be the ideal generated by these kinds of operators. We take all possible products such that the J component is compact if J is in the set. This set was the set of all theta J's such that this is 1. So if you take a generator on the J portion, then you take compact operators in that portion. This would guarantee that our algebra is, the sister algebra is commutative modulo of this ideal. And by using that fact, then you can do some tricks there by using the projection onto that sister algebra. And you can prove that the radical of these algebras is in this intersection. So this means that every element from the radical is a limit of some operators such that on the J portion, there is a compact operator. So this is nice, but there is a problem here because you can approximate the operators from here by sums of these projections Qj was here, where J is in the set J theta. So you can approximate, for example, something like this on operator S. But this sum is not orthogonal. So one of the tricks in this case was to find a way such that you can take summands from the sum, even if the sum is not orthogonal. Okay, so in any case, after doing some work, one can prove that the operators from here can be approximated in some sense by operators of the form Q JD, and then some operator S in the radical. Yeah. S in the radical. Then you have to write some sum of these kinds of operators, and so you have to do two things. You have to understand how the operators from the radical of this form look like, and what happens when you take a sum. So this is the two key points for this part. And okay, for that, let me maybe, okay, just I will skip this to just for a minute. This idea of the QJD times a operator on the radical is solved by this trick. It turns out that if you take a element in the radical for some generators given by this theta, then you can decompose it as this sum. We will see what this is, but these operators from the left live in the algebra with theta minus the basic element j. So this means that these operators live in the algebra with one generator less. So you can do some inductive argument and prove that the whole algebra can be understood by considering successive generators. So once this is done, the only thing that remains is to understand who these S are, and then you get a description of the algebra. Okay, I think I'm running out of time. I will just maybe then briefly mention who these H are. So these H are these polynomials that you construct. It's like the minimum thing that you can do such that your operator is in the radical in that finite portion. I mean, you take some j, you take j, so you take one portion of the whole tuple, you take a coordinate d in that tuple, you consider the matrix, and that matrix is this one, and since it's a finite matrix, the spectrum is finite. And so if it were the only thing we have, then you would have a operator in the radical by considering the evaluation on this polynomial. So we could take, for example, here h of t, and then this operator, its Gelfand image is 0 because we are making 0 by taking here all elements from the spectrum. So that's the only trick we are considering here. But it turns out that if you want this to work, you need to do it step by step. So you take one element at a time. And so if you have NJD elements, then you have to take NGD elements from the spectrum. In the case of quasi-homogeneous symbols, for example, as I told you, these were all nilpotent matrices, so these were all just 0. So this whole story about the h is just the polynomial x. So this means that in the next lemmas and constructions, instead of making all these things, it's just like decomposing this as, for example, s of t times some operator s prime, for example, times t, like this. But well, this is the general case. So using this whole decomposition, one can prove the following things. The radical is the image under some projection applied to this ideal. This is also a generalization of some result that was in previous works. In that case, it's almost the same thing, but in that case, instead of this j theta, it was the compact operators. And okay, so this is one way of seeing the radical, and is a consequence. The radical
So
can be
mean,
approximated.
Wait a minute. You mean that left-hand side here is a closed set? Yes, this one.
Yes. Yeah, this is closed.
Okay.
Yeah, this is a closed ideal, and it's just intersected with the algebra. And so, as a consequence of this, the radical can be approximated by the intersection of the radical and this algebra generated of this non-closed algebra of finite sums of finite products. And so what remains is only to understand what happens with this algebra, what this algebra looks like. So what's one of the bad things, because it seems to be very complicated. So by now, I know some important cases, but I have no characterization of the most general case. But I have this. So if m equals 1, which means if you have only one generator, or in the case of quasi-homogeneous symbols, if you have quasi-homogeneous symbols just in one group, or if all matrices are nilpotent, or if the number of eigenvalues of each finite matrix goes to infinity, then this algebra is exactly of this form. Sorry, it's generated by elements who are of this form. So this complicated sum is not that bad. You can just by now ignore this direct sum, and you would have just something like this. You take your h, you evaluate the h in the Toeplitz operator t of c, and then you multiply by the projection. Now, in the general case, you have a sum of these operators, so that's why you have to take some sum like this and to take a product for some diagonal operator like this. The only problem is that it's not really clear that this kind of operator is in the algebra. So that's why this can only be proven by now for these cases. In the general case, it's not clear if this is in the algebra or not. And it is in the algebra if this is finite, which is exactly when one of these things happen. So my conjecture is that this holds in general, but by now I have no proof of that. Okay, then just a last corollary. So this would be in those cases, the radical would be generated by these kinds of operators. And as a corollary, this Banach algebra is semi-simple if and only if all those matrices are diagonalizable in the sense that their Jordan canonical form is diagonal. So they might not be unitarily equivalent to diagonal matrices, but if their Jordan canonical form is diagonal, that is exactly what we need for the algebra to be semi-simple. That explains in some sense why, for example, in the case of this pseudo-homogeneous symbols time x conjugated pseudo-homogeneous, why the radical disappears when x is not 0. So if you take x greater than 0, then the radical in this case is 0. And it is because those matrices can be explicitly written as diagonal matrices by means of invertible matrices, not of unitary matrices, but of invertible matrices. And that small thing that you cannot write them by means of unitary matrices is the reason why this is not a sister algebra. When x is equals to 1, then those matrices are exactly unitary. Okay, so we have this characterization, and well, that's maybe for the next talk. Okay, so I wanted to show some more results, but I guess in the next talk it will be no problem. Okay, so that's what I would like to show you. And thank you. Any questions?
Yes, thanks, Miguel. No problems is not correct words. Yeah, you do have a problem because you planned too much material to say. And
Yeah.
I think that it's not exactly the case that you need only one extra talk. I think you need more. So next talk, please be more, say, flexible, in a sense, not too much material.
Okay,
Because you are willing to present too much in this period of time.
Yeah, I thought I would have time, but yeah.
Yes, so I think at least you need to plan 2 more talks.
Yeah.
And now please questions to Miguel. Wolfram, any words from your side?
Yeah, I agree. So this is partly a bit technical, so I think it's maybe better to slow down at some occasions and give some examples. I have one question concerning this calculation of the radical. So you assume that the symbols are continuous up to the boundary. Can you explain again why that is necessary for your analysis? And what would you do if the symbols were just vanishing oscillation, for example? So probably you dilate them a bit so that they become continuous up to the boundary, and then you let the parameter go to 1 or something like this?
Okay, that continuous property, that continuity property is because of this. That the radical is in this ideal is important because using that you can control the growth of D in this decomposition. And so in some occasion you have to take some sum where D goes to infinity. And if you don't control that growth, then it's not clear how to see where this converges to. So that's why we need this radical to be in this ideal. And for the radical to be in that ideal, so the idea is to take this algebra to think of it as being a subalgebra of, well, it is a subalgebra, the sister algebra generated by it. Then you can take the quotient, both sides, so to say, J theta. And now this algebra is commutative. And so the radical is the 0, which means the radical is this ideal. So
you need a compact semi-commutators.
Yes, exactly.
That's the reason.
Exactly. So you need this algebra to be commutative. So yes, if you replace this continuity by some oscillation property, then this should work also. This would work also. But then there is a problem, because in that case, this result is not holding anymore as far as I know. I mean, maybe it holds, but I'm not really sure how to approximate the points that need to go here to the essential spectrum. Because for the proof of this, we're using some continuity of the symbol. And if you only have some oscillation property, then I think this should work also, but I'm not really sure how. So, yeah.
More questions or comments? So Miguel, next Wednesday we are planning your second talk, and about third talk we will decide later on.
Okay, yeah.
So
Well, then,
next
thank
Wednesday, your second talk, please not be so quick.
okay, yeah.
Yes, give time all of us to think about what are you talking.
Okay, yes. Well, then, thank you, and see you next week.
Yes, so
So
okay.
what will the second talk be about? The
Well,
Hardy space
I
case?
was, yes, I will finish to describe this Bergman space case and maybe to give some other details, and then I will discuss the Hardy space.
Mhm.
Yeah.
Okay, great. So see all of you next Wednesday. Bye-bye.
See you next week.
Goodbye.
See you.